the sun pulled off something downright scary. A huge gash tore open on its face, spewing a torrent of plasma straight at our planet. Right then, the spacefaring Comet 3I Atlas blinked out of sight from all observatories, and our world shook with an earthquake. So, what's everyone wondering now? Did it get obliterated or altered somehow? And if it comes back, what form might it take? While one comet ducks out of view, another steals the show. Comet Leonard, a frozen survivor from before human history began, is hurtling through our heavens. Here's why the coming fortnight will be make or break. Over in China, researchers pulled off what feels like straight-up sci-fi. A bulletproof comm system that's an absolute tattletale. And stay sharp, before we wrap, we'll spotlight the stellar events you can't afford to skip, including one that's flying under the radar but shouldn't. If these enigmas are gripping you like they are me, don't just sit there. Like the video, hit subscribe hard, and keep tuned as these tales play out live. Comment below with your location, the local time, and be real. Do you think we're getting the full scoop on these game-changing finds? If you're keen to boost this crew, spread this clip on X, Facebook, Reddit, or your chat groups. Each share, remark, or tap powers the quest. You're why we keep pursuing these leads. Thanks for joining the chase. Part 1. The Vanishing Act. The Sun Unleashed Pure Terror. October 2025 kicked off with a stellar warning most folks missed entirely. Experts tracking our star grew increasingly alarmed as a gigantic cross-equatorial coronal hole burst wide across the solar disk. A rift in the sun's magnetic shield resembling an injury leaking unseen power into the void. This went way beyond standard solar antics, the sort that sparks stunning northern lights and maybe glitches a handful of satellites. The breach was colossal, stretching over zones in both the sun's northern and southern halves at once. A setup that's uncommon and whose effects we're just starting to grasp. The solar wind surging from this breach in the sun's protective barrier hit velocities of 700 kilometers per second. For context, picture a storm where every bit of air rushes along at close to 1.5 million miles per hour. The rush of ionized bits, protons and electrons yanked from their atomic bonds, barreled at Earth like a stellar pressure washer targeted right at our planet's protective bubble. The setup was spot on, eerily perfect. The magnetic charge of the solar wind lined up exactly with Earth's field in the ideal way for peak interaction, delivering the most intense energy handover from the sun's exhale to our world's magnetic shield. Space weather specialists hustled to forecast the fallout. Utility managers got alerts for their grids. Satellite teams geared up for potential glitches. Aurora enthusiasts grabbed their gear and raced northward, anticipating a sky lit up in hues beyond words. Yet another twist unfolded precisely then. A development that shifted this sun flare from everyday space weather to a true interstellar puzzle. Comet 3I Atlas, merely the second verified outsider comet spotted in our solar system, slipped behind the sun. Seconds earlier, it lingered as a dim glow tracing a path from some distant star, hauling frosty debris and stones born in foreign nebulae around a star we'll never witness. Seconds later, it dissolved into the sun's blaze, engulfed by our star's blinding light, undetectable to any ground or orbit-based scope. The coincidence was too stark to brush off. With Earth's shield battered by the quickest solar gusts in months, and at the same instant, our sole reachable cosmic envoy fading out courtesy of the very trigger of that barrage. Researchers, ever cautious and drilled to dodge rash assumptions, stuck to the line that links don't prove causes. They picked their statements with precision when journalists probed for ties between these occurrences. That's when the quakes hit. A series of magnitude 7 jolts rocked various spots on the globe mere hours after the solar wind's onslaught. Sensors captured the fierce vibrations, the abrupt unleashing of pent-up geological force that had simmered in the strained crust underfoot for years, maybe longer. In raw numbers, such shakes aren't shocking. Our planet sees about 15 magnitude 7 events annually on average. Still, seeing multiple clusters so near a big solar flare and an interstellar object's fade-out ignited our innate drive to spot patterns, that primal brain circuit forever hunting for ties. Connections that seek significance in mere chance. Might the sun's magnetic barrage against Earth have somehow sparked geological unrest? The prevailing scientific view insists otherwise, that's not the mechanism behind seismic events. Tectonic plates remain indifferent to magnetic influences or solar streams. They shift and fracture based on principles of rock dynamics and built-up stress. Yet alternative perspectives persist, from scientists on the edges of geophysics who highlight odd patterns in quake occurrences amid solar peaks, proposing links via ionospheric interactions or slight alterations in Earth's spin. Such concepts haven't secured a foothold in vetted journals, though they echo in academic gatherings and digital discussions. Quiet hypotheses that the establishment hasn't fully refuted for all. The comet, however, holds the true enigma. 3I/Atlas secured its label as the third verified interstellar body spotted traversing our solar system. The initial one was 1I/Oumuamua in 2017, that odd cigar-shaped entity that rolled through the inner realms and showed speed up not entirely accounted for by standard comet venting. The follow-up was 2I/Borisov in 2019, which resembled the icy rock visitors we know, a comforting clump of frost and grit adhering to expected trajectories. 3I/Atlas surfaced in 2025, monitored as it plunged sunward along a hyperbolic path, traveling at speeds defying capture by our star's pull. Undoubtedly an outsider merely slicing through en route to the void beyond stars. These wanderers prove invaluable to research. They offer our sole glimpses of matter from distant star systems, pending advances in spacecraft that could journey to neighboring suns and haul back tangible artifacts, a feat beyond our era. Each ray of light harvested from such a cosmic drifter conveys details on molecular makeup, on the makeup of nascent planetary rings orbiting foreign stars, on if the forces shaping our own system are commonplace or singular. As 3I/Atlas vanished behind the sun, our chance to harvest that insight paused, at minimum. The puzzle now gripping stargazers is more straightforward, yet more unnerving than musings on solar gusts or tremors. Upon 3I/Atlas reappearing from solar shadow, if it does, will we even identify the entity that returns? Has the sun simply devoured our extraterrestrial guest? Might the fierce warmth, radiation, and magnetic chaos close to our star have remolded it, shattered it, or erased it to vapor? Discovery looms, and the revelation could overturn our assumptions about these stellar nomads. Part 2. The Wanderer. We forfeited. The tale of 3I/Atlas unfolds much like typical comet finds, rooted in vigilance, with robotic scopes sweeping the heavens nightly in search of stellar outliers. The Atlas Project, acronym for Asteroid Terrestrial Impact Last Alert System, deploys 4 automated observatories worldwide, mainly to detect rocks that could threaten our planet with impacts. Yet these instruments capture all motion indifferently, comets included. During the opening stretch of 2025, they ensnared an exceptional find. The intruder first showed as a dim blur in feeds from the Hawaii outposts. Subsequent checks from additional sites verified its swift transit. Path projections uncovered the hallmark of a hyperbolic arc, with eccentricity exceeding unity, signaling this wasn't tethered to the sun. It hailed from afar. Post its solar near miss, it would depart, venturing anew into the interstellar expanse. Its path's vigor marked it as no solar system offspring. This was from beyond. The astronomical network sprang into action swiftly. Prized observing slots, usually booked far ahead amid fierce rivalry, opened up overnight. Spectral examination, probing the wavelengths bounced or radiated by the comet, took center stage. What comprised this anomaly? Did it harbor the familiar blend of water frost, CO2 frost, and carbon-based compounds typical of homegrown comets? Or might its makeup expose otherworldly reactions, elemental proportions hinting at genesis near an alien stellar type? Initial readings hinted at a conundrum. 3I/Atlas's luminosity didn't follow the anticipated pattern. Ordinarily, comets glow brighter nearing the sun, tracing a standard arc tied to escalating ice evaporation. With solar warmth ramping up, H2O ice begins to sublimate, shifting straight from solid to vapor as rays heat the crust to roughly 200 Kelvin. Additional gases like CO and CO2 evaporate at cooler thresholds, sparking effects far from the star. The light from the sun revealed an unexpected pattern in the brightness of Comet 3I/Atlas, with phases of minimal increase that fell short of theoretical expectations, interspersed with abrupt surges in brilliance hinting at sporadic ejections of material like dust or vapor. In certain images, the surrounding envelope of gas and particles, the coma, looked surprisingly dim. The amount of dust generated appeared subdued compared to what one might anticipate from an object of its scale. A few scientists proposed that the core could be unusually compact, dominated by rock over frozen water, accounting for the subdued outbursts. In contrast, others theorized the reverse, a highly spongy interior, akin to a loosely aggregated heap sustained by feeble gravitational pull, leading to erratic vaporization of ice instead of consistent release. Adding to the puzzle were the subtle influences beyond gravity. Cometary paths deviate from strict Keplerian trajectories shaped purely by solar pull. As frozen elements turn directly to gas at the core, they form streams that function as minuscule thrusters, nudging the body away from its forecasted route. Though minor, these extra gravitational effects are detectable and complicate forecasts of a comet's precise position at any moment. For 3I/Atlas, simulating these deviations proved especially challenging. Orbital estimates underwent repeated adjustments, with margins of error constantly evolving, leaving observers more and more doubtful about the exact timing and location of its return from solar obscurity. A few sightings suggested potential breakup prior to vanishing. The hearts of comets are delicate assemblies, loosely knit groupings of frozen volatiles and stones susceptible to splitting from heat or gravitational tides. Such disintegration typically yields a sequence of fragments tracing parallel paths, occasionally manifesting as distinct clumps within the envelope. Photographs of 3I/Atlas displayed hints of imbalance, stretched forms that could signal the onset of structural failure. Should fragmentation have started before it slipped behind the sun, the stakes rise sharply. Emerging from the blaze might not be one cohesive form, but rather a trail of rubble, or possibly nothing detectable if the pieces dwindled too fine. Parallels to earlier extrasolar intruders were unavoidable. The Pioneer, 1I/Oumuamua, eluded clear classification as a comet. It lacked any evident envelope, dust stream, or hallmark of frozen composition. Still, its post-solar speed-up defied gravity alone, without gassing from unfamiliar ices, perhaps carbon monoxide or nitrogen, offering the best fit, though without the telltale dust signature. Wild ideas like solar sails or extraterrestrial artifacts sparked widespread fascination, but garnered scant backing from experts grounded in data over conjecture. Meanwhile, 2I/Borisov acted more like a conventional solar system wanderer, sporting a clear envelope and tail, plus luminosity shifts aligning with typical models. Its makeup included water gas and carbon monoxide, echoing the makeup of local comets, a comforting sign that star systems elsewhere craft comparable wanderers under shared principles. Yet Borisov too exhibited breakup cues at perihelion, its sunward plunge, with shots revealing a fragment detaching from the primary core. A stark warning that these cosmic migrants often don't endure the inner system's rigors unscathed. 3I/Atlas now traced a comparable course, hurtling sunward, only to vanish at the most inopportune juncture. Solar conjunctions alignment, placing the body earthward of the sun, imposes a viewing blackout lasting days to weeks, based on path and visibility. For a dim wanderer already displaying quirks, this void turns into an enigma, a span ripe for unforeseen developments beyond our grasp. Disintegration might unfold, a sudden flare-up could occur, or it might hold together, merely overwhelmed by solar dazzle. Clarity awaits its return, assuming one happens. Simulations tried forecasting outcomes from presumed core dimensions and makeup. A sizable, stone-heavy nucleus would likely weather the heat with scan erosion per thermal projections. A diminutive, ice-rich one might fully evaporate near closest solar approach, yielding only fading vapors and particles. Estimates of the core's extent varied wildly, from hundreds of meters to kilometers, a tenfold spread that rippled into all projections, reducing them to educated gambles. Experts repeatedly invoked the term unseen extrasolar voyager, lurking out of sight amid the sun's blinding radiance, beyond the reach of all our telescopes. An interstellar visitor from a distant star system hung in a precarious balance between endurance and demise, leaving us powerless except to observe and speculate about its eventual reveal once the orbital alignment permitted visibility anew. That burden dragged on like ages squeezed into mere days. Chapter 3, where stellar gusts clash with extraterrestrial frost. The sun isn't some mild benefactor. We often picture it as our nurturing celestial body, the cozy glow that sustains life on our planet. Yet in proximity, it's a tempestuous, turbulent sphere of superheated gases, with temps soaring to millions of degrees and magnetic forces contorting into setups that hoard power akin to coiled mechanisms ready to unleash. When those mechanisms release, the fallout can devastate whatever lies close by. The coronal gap that appeared in October 2025 ranked among those incidents that unsettle experts in solar dynamics. Such gaps form where the sun's magnetic lines extend outward into the void instead of curving back to the photosphere. These extended lines serve as conduits for solar wind, letting charged particles stream out at elevated velocities across the heliosphere. Normal solar wind clocks in at about 400 kilometers per second, but from this specific gap, it surged at 700 kilometers per second, almost double the pace, packing greater force, heightened vigor, and amplified risk of interference. When such rapid solar wind collides with a comet, the encounter turns intricate and ferocious. Comets lack the magnetic barrier that shields our world. No magnetosphere to repel the incoming ions. Rather, the wind crashes straight into the enveloping coma. That hazy envelope of vapors and particles around the core triggers bizarre physical reactions. Ultraviolet rays from the sun ionize the coma's gases, generating a swarm of charged particles. These respond to magnetic influences, and the wind embeds rigid field lines that wrap the comet like a shroud. What emerges is a magnetotail, shaped by the clash between the wind's field and the comet's ionized output. This appendage can stretch for millions of kilometers in the direction away from the sun, shimmering subtly from the emissions of ionized carbon monoxide and similar compounds. Far from inert, the tail undulates and ripples due to eddies in the solar wind. At times, full detachments happen, severing the tail and prompting a fresh one to develop. Telescopes on Earth can spot these with proper gear, offering insights into the wind's state and the comet's output of gases. Yet consider a comet facing such swift solar wind while already strained by fierce solar proximity at perihelion. Past cases offer chilling precedents. Comet Ison, spotted in 2012 and forecast for dazzling visibility, shattered on its solar skim in 2013. Probes monitoring the sun captured it approaching perihelion as a vivid form and exiting as mere scattering debris. The core evidently fragmented utterly. Overwhelmed by heat and gravitational pulls, Comet Lovejoy, a sun grazer that ventured within 140,000 kilometers of the sun's face in 2011, defied expectations of obliteration and persisted. Snapshots revealed its tail unfurling for millions of kilometers post-perihelion, fueled by enormous vapor releases from the intensely warmed core. Lovejoy's resilience caught everyone off guard and remains partly mysterious. A mix of core dimensions, makeup, and internal fortitude evidently let it weather temperatures that ought to have evaporated it. 3-2 Atlas wasn't venturing quite as near the sun as those daring grazes, yet it was crossing into the zone of profound solar sway, right amid a spell of atypically fierce solar wind. The puzzle arose: could the blend of heat strain, radiation exposure, wind battering, and maybe earlier splintering prove fatal? A few scientists floated bolder ideas. The electrical comet theory, championed by a niche cadre of plasma specialists, argues that comets build up electrical potentials amid solar wind contacts, with such forces, not merely thermal evaporation, propelling their displays. Orthodox astronomers reject this view, arguing standard mechanics account for sightings without electrical twists. Still, advocates cite tail severances and abrupt luminosity shifts as signs of electric involvement. The idea veers into unconventional realms, positing that potent solar wind bursts might spark charge imbalances in the coma, potentially leading, under rare conditions, to sudden bursts or path deviations exceeding typical gas expulsion. Proof for these assertions remains debated. The conceptual basis, although the research remains unfinished, these concepts keep gaining traction as they strive to account for anomalies that challenge conventional theories. During a significant solar wind episode, when 3 Atlas vanished from view, proponents of the electrical comet hypothesis viewed it as a possible validation of their theories. Conventional scientists, however, regarded it as a regrettable yet mere chance alignment of occurrences. Adding to the ambiguity is our lack of precise knowledge about 3 Atlas's makeup. Pre-disappearance spectral data was sparse and failed to yield a full breakdown of its components. The object might primarily consist of water ice, akin to numerous comets in our solar system. Alternatively, it could be dominated by carbon monoxide ice, which vaporizes at far cooler temperatures and might trigger outbursts farther from the sun. Or perhaps it's laden with silicates and scarce and volatile materials, resembling an asteroid more than a standard comet. Various makeup profiles would react distinctively to solar warmth and particle stream influences. Should the core be highly porous, nearly akin to aerogel, with a density scarcely exceeding that of the surrounding gaseous envelope, heat pulses could infiltrate profoundly, warming interior ices and possibly triggering a chain reaction of vaporization that shatters the whole body. If a protective layer of dust coats much of the core's exterior, outgassing would focus on select dynamic zones, generating streams that might accelerate the core's spin or alter its tumble in erratic fashions. In the case of a contact binary structure, 2 lumps bound by feeble self-attraction, gravitational pulls and heat-induced strains might wrench it asunder. Here, the sun acts as a celestial sentinel, a disruptive power that challenges every body venturing into the solar system's core realms. Comets from beyond our system, born in alien settings with potentially divergent builds compared to local ones, could prove especially susceptible, or conversely, more resilient, shaped by harsher origins that fortified them. Clarity will come only with fresh sightings. Drawing parallels to Comet Shoemaker-Levy 9 offers valuable insight. That body was ripped asunder by Jupiter's gravitational shear on a near flyby in 1992, splintering into over 20 pieces that subsequently slammed into the gas giant in a dramatic barrage of collisions. The breakup occurred because the planet's pull varied so sharply across the comet's span that it overpowered the object's internal cohesion, effectively tearing it to bits. At the range where 3 Atlas traversed, the sun's gravitational gradients are far milder. Yet a body already compromised by heat damage or earlier splits could yield to stresses that a sturdy core would shrug off. Has the sun exposed a chilling truth about wanderers from interstellar space? Resolution hinges on the comet's return from behind the sun. Should 3 Atlas materialize whole, pursuing its hyperbolic path with typical emissions of gas and particles, the solar wind incident fades to a mere aside, a fluke that fueled debate but held no deeper import. If instead it has fragmented or faded entirely, we confront unsettling inquiries. Are extrasolar bodies inherently more delicate than our frameworks suggest? Does their genesis or architecture render them prey to solar battering in unforeseen manners? Part 4. The waiting game commences. Skywatchers are noting dates, reviewing orbital paths, and devising viewing strategies for when 3 Atlas ought to resurface. The schedule hinges on multiple variables, such as the precise route, complicated by non-gravitational effects, its luminosity, which may have shifted profoundly, and the sightline setup, dictating the solar distance required before instruments can pick it out from the celestial glow. Estimates indicate emergence from solar alignment around late October or early November 2025, achieving adequate elongation, the apparent angle from the sun as observed from our planet, for detection via advanced tools. Early hunts will probably rely on orbital platforms better equipped to shield against solar glare than terrestrial scopes. SOHO, the Solar and Heliospheric Observatory, features coronagraphs that simulate eclipses to peer into the sun's vicinity, a common refuge for sun-grazing wanderers. STEREO, the Solar-Terrestrial Relations Observatory with its pair of sun-circling probes, offers alternate perspectives that could spot the comet sooner than ground views. The Parker Solar Probe, our boldest venture toward the sun, traces a path that occasionally dips inside Mercury's orbit through zones of blistering solar wind velocities and heats. If its course aligned closely with 3 Atlas amid the conjunction, the craft sensors could have snagged readings on the object under extremes no Earthbound setup could match. The Parker Solar Probe isn't equipped to spot comets in the vast expanse it can scan. Its primary goals center on examining the sun's corona and the solar wind, rather than icy wanderers like these. Without the comet crossing into the spacecraft's limited line of sight precisely when needed, we won't capture any insights from that pivotal phase. The mission team hasn't reported any lucky alignments, implying the orbits didn't match up or the object was too dim to register amid the sun's glaring light for the probe sensors. What might the initial post-encounter snapshots reveal? In the optimal outcome, the comet materializes much as anticipated, maybe a touch dimmer from shedding dust, yet largely whole, displaying a clear envelope of gas and a streaming tail that signals ongoing ice evaporation from its core. The light spectrum would display the usual traces of water vapor, cyanogen, and carbon monoxide, those chemical hallmarks verifying its makeup. Details on the tail's extent and form could yield clues about the pace of gas release and the state of the solar wind right after the close pass. Experts would gauge its luminosity, stack it against earlier measurements, and evaluate if substantial material was shed during the sun's nearest pull. On the flip side, the area could stay blank. No sign of 3 Atlas in the expected spot, hinting at total breakup. The core might have shattered into tiny bits too faint to pick out one by one or evaporated away completely, resulting in just a thinning haze of vapors undetectable as a solid body. Such a result would sting for research purposes, though it's far from rare. Plenty of comets have vanished following tight solar grazes, adding to our knowledge of how these objects shatter. Shades of gray fill the space between. It might come back in chunks, a trail of clumps tracing the path that shows the core divided but the parts endured. Tracking these debris trains proves tricky since each segment glows weaker than the parent body, yet they offer key details on the core's build and the dynamics of splitting. Should 3 Atlas re-emerge in pieces, researchers would calculate the gaps and speeds between them to piece together the timing and nature of the split. Yet another option is a quiet phase. The close sunswing could have burned off the outer layer of ices, forming a tough, shadowed shell that blocks more outgassing until heat fractures it or where reveals new frost. Inactive comets mimic stony asteroids, lacking any gas halo or streamer, just a stark surface bouncing back rays. A dormant 3 Atlas would rob us of gas analysis chances, but enrich our grasp of crust evolution and protective layers. The most captivating twist would be an unforeseen surge in shine. Occasionally, comets crack open to bare untouched, ice-laden zones to the sun, sparking bursts of vapor output and glow. A breaking core might uncover extra zones of activity, boosting the overall melting area. If 3 Atlas splits and flares up at once, the survivor could outshine its prior self. Even scattered, though, it would probably dim fast as the many pieces exhaust their frosts. Breaking down the light will prove essential. Prior scans caught hints of water and maybe carbon monoxide, but a full chemical map was elusive. Fresh spectral checks after could uncover elements overlooked before, perhaps not prominent then or scanned at wrong bands. Oxygen glows would flag water release. Cyanogens CN flags carbon-nitrogen reactions. Traces of sodium and iron occasionally surface in these visitors, signaling deep core metals laid bare. Backyard stargazers can contribute to spotting it anew. A worldwide web of home setups offers round-the-clock monitoring that big observatories, bound by slots and plans, can't rival. Should 3 Atlas flare surprisingly or scatter into distant shards, hobbyists could lead the discovery. Citizen science in the stars has surged, with tech like digital imagers and apps letting enthusiasts deliver pro-level data. This stellar puzzle plays out live, and anyone with gear under open skies can join in. Assuming it made it through, 3 Atlas might pop up anytime, or days, then months, might drag by with silence until observers accept it's lost. The sun claimed it after such a long trek. The suspense blends frustration and thrill perfectly. No craft was dispatched to chase it down. Our hunt is limited to aiming scopes and waiting. We point our scopes toward the forecasted spot and simply observe. There's little else but to gaze in anticipation and brace for whatever materializes amid the sun's intense glow. This larger dilemma preoccupies astronomers everywhere. Without its core, does 3I/Atlas still count as one of our trio? Or has it become mere rubble, a scattered haze of particles and vapors that used to form an extrasolar wanderer, yet no longer counts as a single entity? On a deeper level, it mirrors the ship of Theseus' riddle. If all the timbers in a vessel get swapped out gradually, does it remain the identical craft? When a comet shatters into countless fragments, each tracing almost the exact path, bearing remnants of the initial core, do they together still embody the comet, or has it fundamentally ended? No official criteria settle this debate. It boils down to tradition and practicality, with experts offering varied responses based on their viewpoints. Yet the issue carries weight since 3I/Atlas symbolizes a rare and invaluable treasure, a fragment from a foreign stellar realm. Its loss stings beyond mere scientific forfeiture. It evokes the severing of a vital bond to immense, far-off realms, a filament tying us to the broader cosmos, cut short just as we began to comprehend its significance. Part 5. When chance morphs into intrigue. Why should this resonate outside the pages of planetary studies publications or stargazing symposia? Humans thrive on spotting patterns, a trait honed by evolution to detect links and coincidences, forging ties even amid randomness. The overlap of a massive solar outburst, an interstellar comet's vanishing act, and several potent seismic upheavals worldwide sets off every instinct in our shared psyche, yelling that forces are at play. Established science firmly rejects ties between solar dynamics and terrestrial quakes. Seisms stem from tectonic shifts, the gradual, relentless drift of crustal slabs atop the churning underlayers, plus built-up tension in the rocks that finally overcomes the grip of fault lines. Solar influences lack any credible way to spark such outbursts. Geomagnetic forces can't sway stone. Charged solar particles get halted far above ground by the planetary shield and air layers. The warmth from sunlight pales against the planet's core-generated heat. Scrutinies of quake records for links to sunspot rhythms or specific flares yield only random noise, nothing systematic. Still, intriguing alignments pop up in datasets, subtle designs hovering just shy of true probability, refusing to fade entirely. A few fringe investigators persist in probing potential pathways. Might solar-induced ripples in the upper air alter the charge dynamics along fracture zones? Could minor tweaks to the planet's spin or field alignment, nudged by solar particle push, subtly amplify crustal pressures, too faint for direct detection, but enough to nudge a teetering fault over the edge? Is there perhaps an electromagnetic interplay linking the upper atmosphere to conductive strata below, channeling forces via mechanisms beyond our grasp? Such notions draw heavy doubt, as bold assertions demand ironclad proof, and the available hints fall short. But our brains don't hinge on p-values. They crave tales, weaving scattered happenings into logical arcs. With solar flares raging, quakes rumbling, and a comet fading all in the spotlight at once, the storyline crafts itself, regardless of whether the underlying laws align. The extraterrestrial essence of 3I/Atlas layers on extra enigma and conjecture. Such visitors hail from beyond our sun's domain, born in realms we scarcely fathom, crafted from stuff whose makeup and atomic signatures may stray from local standards. They're truly otherworldly, in the strictest definition. Throughout history, we've cast our dreams and dreads upon the strange and unexplored. When Oumuamua showed thrust defying easy dismissal as routine ice vapor release, buzz exploded over-engineered sources. Extraterrestrial scouts scanning us, tech surpassing our ken. The plainest account stayed rooted in nature, yet the probe theory gripped the masses, fulfilling urges that bland reports on gas evaporation couldn't sate. 3I/Atlas dissolving in a solar tempest sparks parallel musings. Does this comet bear some encoded secret rendering at a mark? Are we seeing an interstellar safeguard measure? The sun neutralizing inbound hazards from Bayo interstellar visitors must navigate vast distances before entering our inner solar realm. The sheer scientific implausibility of such notions fails to erode their emotional draw. We crave a cosmos filled with enigmas beyond mere orbital paths and spectral analysis. We seek profound secrets in the stars' configurations. We yearn for comets to transcend mere icy debris. We envision them as heralds, bearers of knowledge, vitality, or intent. The concept of panspermia, that life propagates across the stars via comets and asteroids, lends a veneer of legitimacy to these longings. Should comets have transported the organic building blocks sparking Earth's biology, arriving amid the intense impacts eons ago, then each one turns into a possible vessel for seeds, with those from beyond our system holding special value for potentially transporting compounds from alien life zones. The demise of 3I Atlas, assuming it occurred, would equate to obliterating a vital specimen, a repository raised before its secrets could be unlocked. Wilder speculations thrive in alternative circles. Advocates of the electric universe view the sun's encounter with the comet as proof of overlooked plasma dynamics. They highlight the object's erratic luminosity shifts, the intense solar breeze, and detachment incidents from past comet encounters, insisting these demand electric interpretations over conventional gravitational and heat-based ones. Their equations seldom hold up under examination. Forecasts frequently diverge from real data, yet the instinctive allure of electricity as a cosmic driver endures. The spectacle of bolts and discharges lends staying power to these theories despite their evidential flaws. Inevitably, plots arise. Are agencies concealing readings from the Parker Solar Probe's solar flybys? Did sensors snag photos or readings of 3 Atlas amid the alignment that leaders withheld? What could drive such concealment? Maybe the comet displayed actions defying explanation, undermining core principles, alarming those grasping the stakes. Perhaps it broke apart in unnatural ways, broadcast signals, or altered its path, hinting at manipulation. Such tales remain extraordinarily improbable, verging on the unattainable. Yet, lack of proof morphs into proof of cover-ups for those skeptical of authority. The role of such theories in psychology stands well documented. They offer mastery, or its semblance, amid unpredictable turmoil. They swap a realm of aimless chance for one of concealed structure and design, even if sinister. Preferring plots beats conceding that quakes hit without pattern, comets shatter pointlessly, or we exist as fleeting minds on a vulnerable planet racing through an uncaring void. Tales of veiled insights and quashed realities satisfy the heart more than chronicles of methodical inquiry inching toward provisional insights. Yet consider this. Occasionally, the stars align in patterns bucking odds. Now and then, alignments feel too precise to ignore, causation aside. The October 2025 overlap, solar flare, comet vanishing, seismic activity, could precisely embody that, a happenstance so rare it warrants scrutiny, even if it signifies zilch in the end. Or it might signal nascent links we haven't grasped yet, subtle ties between earthly forces and cosmic weather functioning beneath our sensing limits. Inquiry advances through probing oddities, not brushing them off. Those probing sunquake links pursue valid, though tentative, research. They'll likely uncover naught, but the pursuit merits effort. Upon 3 Atlas reappearing from solar shadow, if it does, we might not identify it. The inbound wanderer may differ from the outbound one. As stargazers share their physics-rooted, chemistry-based, trajectory-driven breakdowns of sightings, some will embrace them and proceed. Others will persist in hunting arcane links tying the comet, quakes, and solar outburst beyond physical triggers. Each reaction feels profoundly human. Each mirrors innate urges to decode our role in a universe brimming with puzzles over solutions. The sun unleashed something fearsome, a comet dissolved, the ground trembled, and beneath those happenings, truth lingers, instilling equal parts awe and disquiet. Part 6. The Visible Comet. As 3 Atlas hides coyly behind the sun, a different comet delivers a spectacle you can truly observe, as assuming you're aware of the right spots to scan and prepared to rise early before sunrise or linger late after dusk. Comet C/2025A6, spotted by Arizona's Mount Lemmon Observatory and thus dubbed Lemon, is nearing its nearest pass by the sun, achieving illumination that makes it detectable via binoculars or modest telescopes, and perhaps even unaided eyesight for those in remote, unlit areas. The coming fortnight offers the prime opportunity for observation. It's perihelion, the tightest solar approach, arrives in mid-November 2025, yet the orbital path positions it for peak earthly visibility just prior to that point, when it's distant enough from solar interference to watch without strain. Right now, the comet graces the eastern pre-dawn heavens, ascending several hours ahead of sunrise, radiating the gentle, hazy glow typical of a lively comet boasting a prominent coma and maybe a brief tail. Projections for its current brightness peg Lemon at magnitude 4 to 5, teetering on the edge of bare eye detection. Under ideal circumstances, the eye discerns down to magnitude 6. Magnitude 4 ought to stand out clearly beyond urban glow, although spotting it sans optics demands precise knowledge of its position. Presently, it's traversing the constellation Cancer, drifting eastward amid the stellar backdrop, with online finder maps illustrating its route alongside familiar star configurations. Spotting comets demands endurance and pitch-black skies. In contrast to planets, which show as sharp dots or disks, comets form nebulous entities. Their illumination disperses over a broad expanse. This scattered quality renders them more vulnerable to artificial lighting and atmospheric factors than concentrated sources of equivalent total luminosity. A magnitude 4 comet fades utterly in illuminated suburban settings where magnitude 4 stars shine steadily. Achieving a clear view means venturing from city centers to sites where the Milky Way arches vividly above, enabling your vision to pick out spread-out, dim-surfaced phenomena. Binoculars serve as the perfect tool for comet gazing. They deliver sufficient enlargement to gather the comet's glow while offering a broad vista that simplifies locating and following the target. The 7x50 variety, a staple for hobbyist stargazers and outdoor enthusiasts alike, performs exceptionally. Secure them to a tripod whenever feasible to steady your grip and extend comfortable observation sessions. The comet will manifest as a compact, hazy blotch, unmistakably unlike a star, potentially tinged with green from diatomic carbon emissions within the coma. Telescopes uncover finer particulars, displaying the coma's form, any streams or sprays of matter from active spots on the core, and the tail if it's grown prominent enough. However, greater zoom restricts the sight line, complicating the initial search and ongoing alignment as our planet's spin shifts it overhead. Plenty of seasoned comet watchers favor binoculars for their visual appeal. The expansive perspective frames the comet amid star clusters and the galactic band, underscoring its role as a fleeting guest amid enduring cosmic backdrops. Initial sightings of Lemon uncovered an aspect that both thrills and concerns comet researchers equally. Its luminosity didn't align precisely with forecast simulations. Forecasting comet brilliance proves challenging due to reliance on immeasurable elements such as core dimensions, makeup, spin dynamics, crustal traits, and dust-gas proportions. Simulations rely on averages from prior comets for these variables, yet each one frequently strays from norms. Lemon displayed phases of accelerated glow beyond projections, then stalls where intensity held steady even as solar proximity shrank. Such irregularities might stem from various occurrences. Sudden flares, involving abrupt revelation of pristine icy substances that spike vapor and particle output, can spark swift surges in shine. The core's turning, exposing varied sides to daylight if one proves more reactive, yields rhythmic fluctuations in light. Or, more alarmingly, these shifts might herald initial breakup, with the nucleus starting to fracture from heat or gravitational pressures. Disintegration poses the stealthy threat shadowing all comet outlooks. A comet might progress steadily, adhering to anticipated patterns en route to perihelion and seeming robust in all ways, only to abruptly disintegrate. The unraveling can unfold swiftly or slowly. At times, a sizable fragment detaches to create a distinct clump beside the primary body. Other instances see the whole nucleus begin to emerge into a swarm of tiny debris pieces, each too dim on its own to detect, yet together they boost overall luminosity dramatically through their expanded total surface, fueling intensified evaporation. The mechanics of breaking apart hinge on structural durability, heat-induced strain, and rotational dynamics. Comet cores are fragile bodies, resembling packed snowballs more than sturdy stone, bound mainly by their own weak pull plus the binding power from frozen bonds and maybe sticky organic residues. Solar warmth on one face triggers expansion, generating tension. Rotation introduces outward forces that heighten physical pressure, while gas outbursts impart twists that accelerate spin. Eventually, the buildup of strain surpasses the substance's resilience, fissures spread, and the core divides. The evaporation dynamics of lemon introduce extra intricacy. This comet seems propelled equally or primarily by the vaporization of carbon monoxide or dioxide rather than just water. These compounds are far more easily evaporated than water, shifting from ice to vapor at cooler temps and farther from the sun. A comet fueled by carbon monoxide stays lively well past the frost boundary where water stays solid, forming a hazy envelope and trail even in the distant solar reaches. Nearing its closest solar approach as heat climbs, water evaporation dominates, typically shifting activity rhythms and light output. Encounters between the tail and solar particles offer further viewing insights. If lemon grows an ionic tail, it stretches straight opposite the sun, swept by the particle stream like a windsock. The particulate tail arcs in a bend, grains propelled by sunlight's push but holding onto their launch trajectory from the core. These dual tail forms, gaseous ions and solid dust, frequently diverge into clear formations caught in images. The ion version glows blue from charged carbon monoxide glow, linear with occasional streaks and clumps from solar magnetic fluctuations. The dust version shines pale yellow from bounced sunlight, wider and hazier, arching softly from the core. Contrasting lemon with 2I/Borisov underscores key contrasts between homegrown solar system wanderers and those from beyond. Lemon originated about 4.6 to 6 billion years back in the swirling gas and grit around the infant sun, likely in the chilly zone past Neptune, where water and other ices could solidify. Tugs from massive planets later flung it into the Oort cloud, that enormous bubble of comets encircling our system, out to 100,000 Australian dollars. An event, maybe a nearby star's pull or a huge gas cloud, disrupted Lemon's path, hurling it sunward on the path we're tracking now. Its makeup echoes ancient solar system mixes, with isotope balances and chemical mixes from our galaxy neighborhood 4 billion years past. 2I/Borisov arose elsewhere, orbiting another sun under potentially alike or wildly varying setups. The heat and density in its birth disk, levels of dense elements, radiant surroundings, sequence of world building, all shaping icy body makeup and form. Matching outsider comets against locals is like examining relics from varied star birthing grounds, seeking shared traits that signal cosmic constants and variances that spotlight regional quirks. Lemon acts as a live lesson in cometary vulnerability. Each one risks crumbling on its solar dive. Many weather their sun grays, shed some material to vapor, withdraw to the system's fringes or farther, and hold together. Others shatter spectacularly, staging dazzling displays with splintered cores and swelling grit halos that flare and dim. A handful disintegrate utterly, wiped out so completely that follow-up pursuit proves futile. Observing Lemon in its prime viewing span goes beyond admiring a stunning sky wanderer. It's about seeing a tough survivor, a relic that braved eons in the Oort chill and now faces the solar blaze and rays that could spell its doom, or not. The schedule works out ideally. As 2I/Borisov ducks behind the sun, Lemon steps in as an alternate focus, a distinct icy body we can truly watch and probe. If comets have only been pixels or sketches to you so far, here's your shot. Step out pre-dawn, pick a dim spot, give your vision 10 to 15 minutes to adjust, and sweep the east in Cancer. That hazy glow, if it holds ice crystals that crystallized long before our planet took shape, along with organic compounds from before life emerged, and silicate grains predating Earth itself. What you're witnessing is a harbinger from the solar system's earliest days, yet in just 2 weeks, it'll slip back into obscurity. Its fleeting appearance draws to a close, leaving its ultimate fate, a tale of endurance or breakup, yet to be scripted. Keep your eyes on the heavens while Atlas remains concealed. Part 7. The Swan and its Backdrop. Comets often show up in groups, or so it appears to those monitoring these frozen wanderers. The truth is a bit more routine. Countless comets are circling the sun at different ranges at any moment, the majority too dim to spot without powerful scopes. A handful shine vividly enough to draw in hobbyists, and only occasionally does one dazzle so much that it's plain to the unaided eye and captures widespread notice. The groupings we notice stem from how we observe and the odds of spotting them, yet they do usher in times when sky gazers enjoy several options to track. The year 2025 looks like it's gearing up to be such a stretch. In addition to Lemon and the C/2023 something Atlas. Wait, actually is written, Vanish 3i Atlas, but preceding, yet another, labeled C/2025 R2, Swan, has joined the records. The name Swan nods to the solar wind anisotropies tool on the SOHO satellite, which scans the heavens in ultraviolet light attuned to hydrogen glow. Comets unleash vast hydrogen halos, neutral atoms born as water ice splits under the sun's UV rays. These envelopes escape visible light instruments but flare up in certain UV bands, allowing Swan to pick them out from afar. At times, it flags comets well before Earthbound watchers can see them. C/2025 R2, Swan, was first noted via its hydrogen envelope, that huge unseen shroud encircling the bright core. Subsequent visible light checks verified it and enabled path projections. This comet traces a stretched oval route, reaching its sun closest point in early 2026, coming after Lemon's swing by, but close enough to keep enthusiasts gearing up their gear and schedules. Initial shine forecasts for Swan indicate it could hit magnitude 6 or 7 at peak, ideal for binoculars but unlikely for bare-eye viewing save in ideal conditions. How bright it gets hinges on guesses about its core's dimensions and how active it is, both still up in the air. Certain Swan-found comets have outshone hopes, flaring up as they near the sun. Others fall flat, staying dim and spread out against optimistic outlooks. The surefire path? Observe and hold steady. An exciting angle with fresh comets ties into meteor displays. As a comet nears the sun, it flakes off debris that fans out along its track, forming a particle trail. Should our planet's path cross this debris, the bits crash into the air at speeds of 30 to 70 kilometers per second, burning up in vivid trails known as meteors or falling stars. The regular showers we see yearly, like the August Perseids or December Geminids, come from our world threading through old dust paths from comets that looped by the sun many times, layering grit over ages. Newcomers on their debut inter-system run can spark erratic meteor bursts. The debris isn't yet evened out by cycles or gravitational nudges from planets, so sudden pockets might form. If we thread one of those, meteor counts could surge wildly, yielding a storm of hundreds or thousands per hour. Such spectacles are scarce and tough to forecast, relying on the precise layout of particles we can't gauge firsthand. Swan's path will get refined in the months ahead, letting experts gauge any odds of our orbit meeting its dust trail. Even slim chances of a shower thrill comet and meteor fans alike. Catching a meteor storm ranks as a must-see event, a sky-spanning light show that unfolds maybe once or twice a lifetime. The streaks emanate from a sky spot termed the radiant, where parallel paths seem to converge. In a frenzy, meteors pour from everywhere, flooding the view with light trails that no image can truly convey. Still, for each comet that dazzles as anticipated, many more underwhelm. Comet lore is full of hyped forecasts that bombed, with prospects for stellar shows turning into lackluster specs. Comet Kohoutek in 1973 was tipped to rank among the most brilliant ever, but the comet that was hyped as the event of the century managed only faint glimpses to the unaided eye, leaving countless enthusiasts let down after expectations of a dazzling display. The 2013 comet, anticipated to endure its closest solar approach and flare up brilliantly, crumbled apart instead. Such letdowns instill a sense of caution and highlight the gaps in our grasp of comet dynamics. Comparing the light output patterns of Swan and Lemon will yield valuable insights for researchers in due time. Observing two comets at the same moment amid comparable sunlight exposure enables straightforward assessments of their vigor and the processes driving ice vaporization. Variations in luminosity at similar solar distances point to contrasts in core dimensions, makeup, or outer layers. Should one be rich in water ice while the other relies on carbon monoxide, their behavioral patterns would split in predictable fashions. If fragmentation strikes one but spares the other, it offers hints into structural variances that influence breakup risks. Pitting Swan against Lemon builds dramatic intrigue. Given how often comets falter, might 3 Atlas suffer the same fate? Could aspects of today's solar surroundings be raising the odds against comet endurance? The coronal hole incident in October 2025 might have been an isolated oddity, or it could herald a stretch of heightened solar turbulence endangering any comet venturing near the Sun. The Sun's 11-year cycle nears its peak activity phase, when sunspots and solar eruptions multiply, with faster solar winds and stronger magnetic fields ramping up. Comets hitting perihelion amid this maximum confront tougher trials than those during quieter minimum periods. Historical comet breakups offer stark figures. The 1992 gravitational shredding of comet Shoemaker-Levy 9 by Jupiter, culminating in the stunning 1994 collisions, showed just how devastating tidal stresses can be. Comet 73P/Schwarzmann-Watchman 3 splintered apart in 1995, dividing into numerous segments that drifted wider across later orbits. By 2011, it had shattered into over 60 tracked pieces. A scatter of rubble stretched across thousands of kilometers in its path. Certain shards kept emitting faint gas tails, while others went quiet, their ices exhausted or locked under inert shells. These breakup episodes hold key implications for assessing orbital threats. An intact large comet core seldom endangers Earth, given the tiny odds of a kilometers-wide body colliding with us. Yet a splintering comet spawns scores or hundreds of fragments, each potentially plowing into our atmosphere. Though smaller and less potent than the parent body, these bits collectively boost the chances of one crossing our orbit. The vast majority vaporize safely on entry or sail past harmlessly, but evaluating dangers shifts when confronting a spread-out swarm over a lone target. Looming ahead, the anticipated 2060 comet sighting, poised to be the century's most radiant, frames today's sightings in a broader view. Comets serve as the solar system's erratic timers, surfacing without schedule, glowing inconsistently, and shattering abruptly. They etch moments into our collective memory unlike the steady paths of worlds and stars. One cohort recalls Halley's Comet from 1986, a lackluster sight for many, yet etched in cultural lore. The prior group cherishes Comet Hale-Bopp in 1997, gleaming unaided for months and piercing urban glows. Our era might etch Lemon, Swan, or Three-Eyed Atlas into memory, provided one persists and shines bright enough. Do we face a surge of exceptional comet visits? Long-term tallies of comet finds reveal swings that could signal genuine groupings or just advances in spotting tech. Wider telescope coverage, deeper sensitivities, and broader sky sweeps inevitably uncover more wanderers. The Atlas program, which spotted 3 Atlas, targets Earth-approaching bodies and snags comets incidentally. Efforts like the Catalina Sky Survey, Mount Lemmon Observatory, and Pan-STARRS in Hawaii run non-stop, hunting for movers. Comets surely shift, so they turn up. Yet data teases a possibility. The Oort cloud, that remote comet stockpile, may face nudges dispatching bursts inward from flyby stars, tugs by massive gas clouds in the galaxy, or the sun's bobbing through the Milky Way's disk as it circles the core. Such jolts could dislodge comets. If true, these influxes unfold over millions of years, beyond direct human tracking. Still, fossilized impact clusters in Earth's strata might expose traces of those primordial barrages. Those icy wanderers that pummeled the inner reaches of the solar system amid the age of the dinosaurs, or perhaps even further back in our planet's past. Comets serve as the solar system's erratic timekeeper mainly due to their irregular, unforeseeable trajectories, unlike the steady routes of planets. Planets typically trace almost round orbits, allowing scientists to forecast their locations for hundreds of years ahead with remarkable accuracy. In contrast, comets emerge from the remote voids along sharply elongated paths. Their reappearances, when they happen, might occur after spans of tens, hundreds, or even thousands of years. Certain ones mark their debut, tumbling in for the first time from the Oort cloud. Meanwhile, short-period varieties get captured by Jupiter's pull, drawing them inward on cycles lasting just a handful of years. Such phenomena highlight how the solar system defies any notion of flawless, mechanical precision in its motions. Instead, it's a lively, unpredictable arena where gravitational forces continually reshape paths and introduce unexpected newcomers without fanfare. Part 8. The Indestructible Transmission. As stargazers survey the heavens for incoming comets and monitor the solar breeze, a separate contest from the cosmos plays out in earthly labs and control centers. In 2025, officials in China revealed the finish of the planet's most extensive quantum messaging network, stretching 12,900 kilometers from Beijing to far-flung terrestrial outposts via orbital intermediaries, boasting transmission that's virtually impervious to breaches. This breakthrough stands as a pivotal step in the surge of quantum data advancements. Should it perform as promised, it reshapes the terrain of worldwide information exchange and digital defenses, with ripple effects reaching well past short-term defense or business uses. At its core, quantum key distribution leverages core tenets of quantum physics to spot any snooping. The core idea blends simplicity with the bizarre in perfect balance. Data becomes embedded in the quantum attributes of photons, those solitary light specks sent via fiber optics or across the void linking orbiters to surface sites. Thanks to the quantum no-cloning rule, these attributes defy flawless duplication. Any effort to probe or snag the photons will inevitably alter them in ways that reveal the intrusion. Consequently, communicators using a quantum link can craft secure codes and confirm beyond doubt if interlopers meddled with those codes en route. The method kicks off with paired entangled photons, generated together and linked in a quantum bond where observing one immediately influences its twin, no matter the gulf between them. This effect, once dubbed spooky action at a distance by Einstein, has undergone rigorous lab confirmations and underpins various emerging quantum innovations, from computing to teleportation schemes. In quantum key distribution, such pairings enable partners to forge identical random sequences for locking down messages. Building the gear demands pinpoint exactness. Photons need producing, linking, dispatching, and capturing with scant waste and top-notch reliability. Alignment gear has to sync satellite emitters with earthbound receivers over vast spans of hundreds or thousands of kilometers, adjusting for air distortions, orbital shifts, and planetary spin. Detectors for single photons must capture lone arrivals at speeds of thousands or millions each second, sifting genuine pulses from stray interference and internal glitches. Safeguards against errors handle unavoidable flaws, yet ensure ironclad protection. China's setup relies on the Mischius satellite, orbited in 2016 and honoring a storied Chinese thinker. It circles at about 500 kilometers up, in a sun-synchronous path that aligns periodically with surface facilities for routine links. In each overhead stint, which runs a few minutes, the craft beams entangled photons to match ground pairs, letting them sync up encryption strings. Those strings then shield routine data flows through familiar coding methods, with the quantum path vouching that the strings stayed untampered. The push to 12,900 kilometers marks a major feat of engineering. Past trials spanned less ground or depended on intermediate relays that could, in theory, fall to hacks. Now, it links quantum segments via successive satellite sweeps and sites, delivering seamless safeguards over vast landmasses. Per the Chinese team, this grid already shields official and banking exchanges from today's hacks and tomorrow's codebreakers alike. That final aspect holds vital weight. Today's safeguarding tools, the sort guarding everything from financial deals to secret state exchanges, hinge on math puzzles too tough for standard machines to crack. Factoring handling vast quantities involves factoring large primes and tackling discrete logarithms, operations that demand enormous processing power, making it unfeasible to crack modern codes despite access to the world's quickest supercomputers. However, sufficiently advanced quantum machines could tackle these challenges swiftly, potentially invalidating today's cryptographic standards. Information secured now and stored by opponents might get cracked much later, possibly in years or decades, as quantum tech evolves. Quantum key distribution counters this store now, break later risk by basing protection not on raw computing power, but on core physical laws. Officials in the West, especially in the US and parts of Europe, watch China's advances in quantum messaging with growing unease. According to the 2025 MIT Technology Review Quantum Index, China leads in key areas like quantum messaging and sensing. U.S. initiatives, backed by Department of Energy grants, quantum network prototypes, and DARPA's probes into orbital quantum links, aim to close the distance. Yet China's head start and heavy state funding have widened a quantum divide that alarms military experts and tech policymakers. The broader effects go further than mere tech rivalry. Should quantum links form the core of tomorrow's protected data flows, countries lacking them could suffer serious intel setbacks. Global pacts on quantum progress are still absent. Debates persist over export limits, knowledge sharing, and uniform standards. Certain experts call for joint efforts and collective building of quantum grids as a worldwide utility, much like the Internet grew into a shared global tool. In contrast, some champion gaining an edge through limits and secrecy, treating quantum dominance as a critical national resource not worth dividing. Might orbital quantum setups underpin the next-gen web? Envision fleets of quantum orbiters ensuring worldwide reach, earthbound hubs in key urban centers, and quantum boosters pushing signals past straight-line constraints. Information would move shielded by ever-updating quantum codes, safe from eavesdroppers and tough against unforeseen future threats. Such a framework would blend with current optical fiber systems, forming a mixed traditional quantum setup where quantum paths handle key swaps and regular lines manage the heavy data loads. Speculative theories inevitably swirl around tech this cutting edge and concealed. Quantum key systems need rigorous trials and adjustments, producing stats on light particle flows, sensor performance, and mistake levels. Much of this info stays under wraps or company sealed. Chinese reports outline broad system strengths, but skip the nuts and bolts specifics needed for outside checks or copies. No doubt, Western spy outfits track the effort intently via intercepted signals and other methods to gauge real prowess against official boasts. This lack of transparency sparks doubts on whether the tech delivers as promised or hides flaws kept quiet. Concerns also arise over government oversight risks. A state-run quantum grid across the country grants unmatched power to observe interaction patterns, content aside. The details of connections, who talks to whom, can expose as much as the words exchanged. Pattern scrutiny can map relationships, follow paths, forecast actions. A quantum setup recording all links, every light pulse. Each key creation builds a monitoring web of immense reach. The link to the three-eyed Atlas story draws a compelling comparison. Like comets ferrying signals from distant stars, not through words, but via molecular makeup and element traces, people today craft unbreakable signal carriers over Earth. Both endure tough conditions. Comet structures weathering cosmic voids and stellar blaze. Quantum codes resisting meddlers' grabs. Each stretches limits of feasibility. Comets as ancient physics-forged data vessels. Quantum webs as modern, human-engineered info conduits. Many challenges linger. Today's quantum key speeds, often just kilobits per second, trail way behind standard data rates in gigabits or terabits per second. Expanding quantum grids for web-scale volumes demands huge leaps in light particle delivery, and challenges in quantum networking persist, particularly regarding improved detection capabilities or innovative strategies for quantum communication systems. The phenomenon of decoherence, where quantum characteristics degrade from interactions with the surroundings, imposes inherent constraints on the duration quantum states can persist and the distances they can travel. Satellites mitigate this by functioning in the near vacuum of space, bypassing much of the atmospheric interference. Nevertheless, turbulence in the atmosphere at terrestrial stations continues to impair signal quality. Securing endpoints poses yet another hurdle. While quantum key distribution ensures tamper-proof key exchange, these keys ultimately rely on conventional computers for data encryption and decryption. Should those systems fall victim to viruses, unauthorized physical entry, or covert attacks that exploit electromagnetic leaks or energy usage patterns, the invulnerable quantum keys lose their effectiveness. Overall security hinges on the most vulnerable component. In practical implementations, such vulnerabilities abound. The notion of a quantum space race reflects a core aspect of human behavior and tech progress. Even in exploring and applying the basic principles of physics, rivalry ensues. Quantum mechanics, perhaps the most triumphantly accurate physical framework in history, both predictively and in its tech ramifications, now fuels international rivalries. The very quantum rules that elucidate atomic makeup and molecular connections today safeguard transmissions and hold out prospects for transformative computational abilities. Countries pour billions into quantum studies, driven less by sheer intellectual pursuit than by the prospect that quantum advancements could tip the scales in defense postures and financial dominance over the next several decades. Unresolved are queries about whether this rivalry spurs progress more swiftly than joint efforts might, or if quantum network advantages will distribute worldwide or cluster among select high-tech powers. These uncertainties linger amid the intensifying contest. Part 9. The Internal Circular Economy. At times, scientific breakthroughs emerge that are so startling and counterintuitive they compel a reevaluation of core beliefs about feasibility. The revelation that bioengineers have modified yeast to transform human urine into the bone mineral hydroxyapatite stands as a prime example. Its uses span from healthcare to environmental benefits, while broader ramifications probe ideas of waste repurposing and the astonishing methods by which living organisms can be redesigned to convert one material into another. Urea, the chief nitrogen-bearing element in urine, acts as a metabolic byproduct in mammals. As proteins degrade within the body, their amino acids undergo breakdown, requiring the expulsion of contained nitrogen. Water-dwelling creatures release ammonia outright, a straightforward, low-energy option in an aquatic setting that disperses and dilutes the harmful substance. Terrestrial species encounter difficulties. Ammonia proves excessively hazardous if it builds up, yet preserving water is crucial. Thus, land-based animals developed more elaborate mechanisms. Avian and reptilian species generate uric acid, a largely insoluble substance that solidifies and exits as a semi-solid, curbing fluid expenditure. Mammals generate urea, which dissolves sufficiently for aqueous transport but carries lower toxicity than ammonia, and is eliminated via fluid urine, a balance between hydration needs and toxin clearance. On average, humans generate 1 to 2 liters of urine each day, influenced by hydration levels and metabolism, holding approximately 20 to 30 grams of urea. This equates to about 10 kilograms of urea per individual annually. Scaled to 8 billion worldwide, it yields around 80 million metric tons of urea discharged yearly. Presently, this urea flows into wastewater networks, gets degraded by microbes, or disperses into ecosystems. This novel bioengineering method explores if such waste flows could yield useful products instead. Hydroxyapatite forms the inorganic essence of bones and teeth, a calcium phosphate structure with the formula Ca10PO4 6OH2. It delivers the rigidity and framework that enable skeletal elements to bear loads and shield vital organs. Actual bone functions as a hybrid, hydroxyapatite nanocrystals interwoven with a collagen scaffold, merging mineral strength with the pliability and resilience of protein networks. In medicine, refined hydroxyapatite proves essential for skeletal transplants, tooth replacements, and repair procedures. Today, it derives from synthetic chemistry or extraction from livestock bones, each method constrained by issues in refinement, crystalline form, and expense. The modified yeast technique employs redesign of metabolic routes. Scientists pinpointed the sequence of biochemical steps to derive hydroxyapatite's starting compounds from urea, then integrated the corresponding enzyme-coding genes into yeast. The standard Saccharomyces cerevisiae, familiar from fermentation in beer making and bread production, now harbors artificial biochemical cascades absent in wild forms. Provided with urine as when yeast cells are supplied with URA as a nitrogen supply along with calcium and phosphate ions, they generate hydroxyapatite crystals that settle out and can be collected. This process unfolds through several stages. The enzyme from UR degrades URA into ammonia and carbon dioxide. The ammonia then integrates into pathways for making amino acids, whereas the carbon dioxide, combined with extra calcium and phosphate ions, participates in mineralization processes that yield hydroxyapatite. The exact crystallography of the resulting product, along with the dimensions, form, and cleanliness of the hydroxyapatite crystals, hinges on various reaction parameters such as pH levels, temperature, ion levels, and the engineered pathways in the yeast genetics. Initial findings are encouraging, yielding hydroxyapatite with characteristics akin to natural bone mineral, yet substantial refinements are needed before this method proves viable for healthcare uses. At present, the efficiency and output levels hinder widespread adoption. The yeast yields hydroxyapatite at levels insufficient for industrial scale, necessitating vast bioreactive setups to obtain substantial amounts. Separating the hydroxyapatite from yeast cells, elements of the growth medium, and metabolic residues poses purification hurdles. For medical applications, achieving top-tier purity is essential. Any contaminants like foreign proteins or bacterial endotoxins in the implanted hydroxyapatite might provoke immune reactions or infections. Attaining pharmaceutical-grade purity in a biotech production setup demands strict quality assurance and refining techniques. Still, the prospects are revolutionary. Each year, bone breaks impact millions worldwide. Although many mend on their own, intricate fractures or bone deficits from illness or injury frequently demand grafts or artificial substitutes to aid recovery. Existing bone graft options encompass autografts taken from the patient's body, allografts sourced from cadavers, and synthetic ceramics. All carry limitations. Harvesting autografts involves extra surgical procedures. Allografts pose minor chances of disease spread and rejection by the immune system. Synthetic ceramics may not bond effectively with living bone. Biologically derived hydroxyapatite from waste could emerge as a plentiful, affordable option if the manufacturing and cleaning obstacles are overcome. The dental implant sector offers another key opportunity. Applying hydroxyapatite layers to titanium implants boosts osseointegration, the fusion between the device and jawbone. Today's coatings rely on hydroxyapatite made via energy-heavy, high-heat chemical methods. In contrast, biological synthesis at ambient temperatures in watery environments would cut energy use and emissions, while possibly forming crystal patterns more compatible with biological tissues for superior integration. The environmental advantages go further than the material itself. URA in sewage promotes eutrophication upon discharge into rivers and ocean shores. Surplus nitrogen fuels algal blooms that drain oxygen and form hypoxic areas. By extracting URA and transforming it into a solid mineral, nitrogen is pulled from the waste flow, lessening ecological harm. This approach embodies waste valorization, viewing refuse as a valuable asset instead of mere trash to discard. Debates inevitably arise over incorporating human waste into medical products. Societal stigmas surrounding urine and feces are profound. Rationally, we recognize that refined substances bear no remnants of their beginnings. The calcium in urine-sourced hydroxyapatite is chemically indistinguishable from that of other origins. Post-purification, the substance holds no waste indicators except for its production history. However, emotional barriers persist. Would recipients embrace bone grafts or dental implants derived from urine? Would oversight bodies sanction these for clinical use? Such issues delve into societal norms and views on risk rather than pure science. Space missions offer the most intriguing scenario. Settlers on Mars or extended orbital voyages grapple with scarce resources, making recycling essential. Astronauts generate urine routinely, which holds nitrogen and vital elements needing treatment for reuse or elimination. Turning that urine into functional hydroxyapatite for healing or construction tackles waste handling and resource creation simultaneously. The sealed ecosystems vital for off-world travel compel innovators to maximize reuse and minimize discards. In a dire situation, your own waste might sustain you. Imagine needing a bone graft on Mars with no other hydroxyapatite, but that from the team's urine. Resistance from big pharma to embracing circular biotechnology is more anticipated than proven, as drug and medical device firms benefit from established supply chains, manufacturing processes, and distribution networks. Innovations that challenge conventional industry frameworks encounter pushback, irrespective of their scientific validity. The extent to which opposition emerges against hydroxyapatites sourced from urine hinges on various elements, such as manufacturing expenses, expansion potential, approval procedures, and patent environments. Should the innovation secure patents and fall under the control of dominant companies, integration into markets grows more probable. Conversely, if it risks turning a profitable item into a commonplace commodity, opposition intensifies. The broader insight extends beyond this particular use case. In natural systems, nothing goes to waste. Essential elements loop endlessly through biological communities. What one life form discards nourishes another. Vital energies move forward while materials recur. Early human societies thrived in settings where discarding refuse was straightforward, thanks to sparse populations and efficient environmental breakdown that repurposed nearly all byproducts. The rise of factories and cities shattered these natural loops, generating refuse flows that surpass the planet's innate reclamation abilities. Advances in synthetic biology provide means to reconstruct such loops through human ingenuity, designing life forms to occupy synthetic roles that mimic environmental functions, tailored to societal demands. Transforming urine into a bone-building compound represents merely one instance. Comparable approaches extend to turning carbon dioxide into energy sources, recycled plastics into eco-friendly materials, or farm drainage into useful substances. Humanity is gradually mending the gaps created by our own progress, aligning with the seamless resource economy that evolution refined across eons. Part 10. Beyond bridging species. The behaviors of animals captivate us endlessly, as they mirror mental and affective conditions familiar from our lives, while emerging in beings whose thought processes stay profoundly foreign. Infectious yawning. The effect where observing another yawn sparks an overwhelming compulsion to do the same, had been viewed as confined to people and select highly gregarious mammals, including chimps and canines. A recent research paper showing this effect in zebrafish upends that view and sparks intriguing inquiries into the behavioral evolution and brain processes driving it. These tiny river dwellers from South Asia, favored in labs and household tanks alike, serve as key subjects for exploring how vertebrates grow and act. Their see-through embryos let scientists observe organ development live via magnification. Their genetic makeup is thoroughly mapped, with techniques to alter and track gene functions readily accessible. Compact in size, inexpensive to house, and prolific breeders yielding masses of young, they suit expansive studies perfectly. Yet, no one anticipated their susceptibility to yawn contagion. In the experiment, zebrafish shared side-by-side enclosures with clear barriers for visual contact. Scientists provoked yawning in a single specimen by limiting oxygen, an established prompt across species. Video equipment captured actions from both the initiator and the watchers. Data examination showed that the watching fish yawned far more often post-observation, with patterns indicating true spread rather than random occurrences from uniform surroundings. What makes this startling? Experts believed infectious yawning demanded mirror neurons or analogous brain networks, enabling creatures to internally replay others' movements and feelings. Such systems, prominent in primate neurology and inferred in some sociable mammals, underpin compassion, mimicry-based learning, and mental modeling of intentions. Fish lack the layered brain regions housing mammalian mirror neurons. Their wiring differs at a core level, appearing less complex in certain ways, though far from rudimentary in totality. Finding contagious yawning in zebrafish implies either that the trait bypasses the advanced wiring we presumed essential, or that parallel evolution crafted equivalent mechanisms in fish via wholly distinct structural routes. Brain pathways for yawning in any creature are still not fully mapped. The motion entails synchronized muscle pulls in the mouth, features, neck, and breathing apparatus, yielding the signature wide-open jaw, sharp intake of air, and gradual release. Once started, it feels automatic, hard to override willfully even in situations deeming it improper. Various catalysts include tiredness, disinterest, oxygen scarcity, and viewing yawns in others. This range of initiators points to diverse brain routes funneling into a unified physical response. Among people, the tendency for contagious yawning builds through early years, reaches its height in prime adulthood, and aligns with assessments of empathic traits. Individuals ranking high on sympathy scales respond more swiftly to others' yawns. People on the autism spectrum, who frequently face difficulties in understanding social cues and feeling empathy, tend to exhibit less contagious yawning. Such patterns lend credence to the idea that this type of yawning depends on brain mechanisms linked to social awareness and emotional attunement. However, observing this same response in zebrafish, animals we usually don't associate with empathy or complex social processing, undermines this tidy explanation. The puzzle of evolution grows more intricate when examining how the trait is distributed across species. Contagious yawning occurs in people, chimps, bonobos, canines, and recently in zebrafish. Yet it's either missing or unproven in numerous other animals that have been studied, such as felines, equines, and the majority of avian species. This patchy presence throughout the animal realm points to two possibilities. The trait evolved separately in various lineages on multiple occasions, or it arose very early and was later abandoned in many branches of the tree of life. Both theories fall short of being fully convincing. For something as precise as contagious yawning to emerge through parallel evolution in both warm-blooded creatures and aquatic ones feels improbable without an overlooked adaptive purpose. An early origin demands an account of why countless groups discarded it. Explanations for its role diverge considerably. Some researchers propose that contagious yawning aids in aligning group activities, harmonizing levels of vigilance or focus within social collectives. When a single member senses a shift in surroundings that prompts a yawn, possibly indicating a switch from wakefulness to relaxation, transmitting that cue via imitation fosters unified responses. Schools of fish undeniably demand such harmony. They travel as cohesive packs, pivoting in unison, holding exact distances, and executing joint dodges against dangers. Might contagious yawning form one element of the repertoire that supports this unity? A different theory emphasizes easing tension and strengthening social ties. It posits that yawning could help control stress chemicals or recalibrate brain activity amid group pressures. Witnessing yawns from companions and reciprocating might generate a cycle that allows collectives to jointly alleviate strain. Zebrafish, being gregarious swimmers that form groups in the wild, deal with hierarchies of status, rivalry for partners, and shared watchfulness for predators. Contagious yawning could thus contribute to upholding solidarity during stressful times. Debate revolves around whether the actions seen in zebrafish truly count as yawning, or if they're merely misidentified jaw motions or gill operations. Under typical conditions, fish don't inhale atmospheric oxygen, so the breathing aspect of yawning in land animals lacks a straightforward parallel. The wide-open mouth displayed by zebrafish might fulfill other bodily needs, like enhancing gill airflow or ingesting food. Skeptics contend that absent solid proof of identical brain activations and bodily effects as in land animals' yawns, labeling it contagious yawning imposes human-like qualities on a visually akin but operationally separate action. Advocates respond by highlighting overlapping traits with mammalian yawns, such as its reflexive quality, fixed movement sequence, activation by low oxygen, and proven social spread. While the brain routes may vary between fish and mammals, divided by vast evolutionary timescales, the label of yawning fits if it fulfills comparable purposes and reacts to parallel stimuli. The field of biology abounds with instances of parallel development, where diverse forms achieve alike outcomes. The wings of birds and bats differ structurally, yet perform the same role. Similarly, yawning in fish and mammals might offer parallel adaptations to matching social or bodily demands. Further conjecture ventures into profound evolutionary ground. Does yawn contagion act as a primal cue? A primordial way of signaling that arose before advanced social understanding. The core wiring that renders yawning infectious could have developed soon after vertebrates emerged, enduring over immense geological periods due to its value in synchronizing behaviors in group-living organisms. For it to persist, the trait must confer notable advantages for endurance or breeding, sufficient for evolution to retain the underlying brain structures despite their energy demands. A more unconventional notion, seldom aired in formal papers but murmured in scholarly gatherings, wonders if such syncing extends past single species, maybe bridging major branches of life. As we grasp it now, yawn contagion functions via sensory input. Observing or hearing a yawn sparks brain circuits that induce one's own. Yet wider syncing in the natural world happens via processes we're just starting to unravel. In lab dishes, heart cells align their pulses through electric and molecular cues. In the swampy forests of Southeast Asia, fireflies coordinate their glows over vast numbers of specimens. Individuals. Might there exist profound biological mechanisms of harmony and attunement that show up in the spread of yawning contagion, alongside various other occurrences? This storyline connects to grand universal motifs via the idea of harmony and coordination spanning different levels. Schools of fish operate as unified groups, reacting to one another's motions via lateral line organs that sense shifts in water pressure. Bird flocks pivot in unison, with each bird adhering to basic guidelines on distance and orientation that yield intricate collective formations. On grander levels, planets revolve in harmonic patterns, where gravitational forces align their cycles into whole number proportions. The Jovian satellites Europa, Ganymede, and Io follow a 4:2:1 orbital harmony. Each arrangement recurs predictably. Across vast cosmic expanses, clusters of galaxies shift under shared gravitational pulls. Their motions interconnect over millions of light years. Harmony emerges as a core tenet shaping structures from the molecular realm to the cosmic one. Oscillators, be they neurons pulsing, hearts pulsing, pendulums oscillating, or planets circling, incline toward phase alignment when linked, their tempos adjusting to shared rates. The math behind linked oscillators uncovers striking parallels among vastly diverse physical setups. Yawn contagion could embody a living example of these widespread harmony laws, acting as a communal oscillator that links via watching and sparks synchronized reactions. Human minds and celestial bodies might share more similarities than expected if we refocus from concrete processes to conceptual frameworks. Both qualify as intricate dynamic setups featuring inner architectures, arising traits, and connections to surrounding contexts. Both handle data, albeit through entirely distinct methods and across enormous disparities in size. Minds handle sensory data and produce actions via electrochemical signals through neural webs. Stars handle gravitational data and produce energy emissions via atomic fusion controlled by pressure and heat balance. The comparison falters under close examination, yet it points to profound inquiries regarding intricacy, data handling, and structure throughout the cosmos. The zebrafish research at its heart underscores our scant grasp of animal cognition and actions. Every premise, every so-called settled truth about animal capabilities and limits stays tentative, open to overhaul with fresh findings. We once believed infectious yawning demanded emotional understanding and reflection neurons. Fish evidently overlooked that notion. Which other actions we deem exclusive to humans or mammals could possess more ancient origins or wider prevalence than anticipated? Tool manipulation surfaces in avian species and cephalopods. Socially past-learned practices, what we call culture, thrive in cetaceans and corvids. Self-awareness about cognition displays signs in rodents and marine mammals. The deeper we probe, the clearer it becomes that the lines we sketch between people and fellow creatures, between sophisticated intellects and basic ones, fade upon closer look. Part 2. The rock poised to graze Earth's outer layer. Humanity will etch April 13, 2029, into memory, provided we endure to do so. That day, the asteroid 99,942 Apophis, honoring the old Egyptian spirit of disorder and obscurity, will skim by our world at just 31,000 kilometers away. For context, geostationary orbiters circle at about 35,000 kilometers. Apophis will thread inside the satellite belt, delivering meteorological data, telecom links, and positioning guidance. It'll gleam visibly without aid, a swift traversing the night sky. The inaugural instance in documented annals of an asteroid this large nearing Earth so intimately that everyday viewers can track its transit. Present path projections confirm zero collision threat. The near miss is assured, the path mechanics solidly mapped, yet the course will steer Apophis harmlessly beyond our globe. This assurance stems from years of meticulous tracking and path adjustments. Upon its 2004 detection, early path estimates couldn't dismiss a minor yet real chance of striking during the 2029 flyby. The news sparked momentary societal unease and fervent research focus. Follow-up sightings as the rock traversed its path sharpened the estimates, narrowing the error zone, the swath of potential positions, until the 2029 collision odds vanished entirely. Yet the tale extends beyond 2029. The tight passage will reshape Apophis's path via Earth's gravitational tug. As a space rock nears a world, tidal strains and pull accelerations alter its course, at times sharply. The extent of alteration hinges on proximity and speed differences. Apophis will undergo notable path deviation. Reshaping its orbital journey around the Sun is altering its potential for future crossings near Earth. Forecasts for the upcoming near misses in 2036 and 2068 carry greater uncertainties, as their trajectories hinge on the precise outcomes of the 2029 flyby, outcomes that remain unmeasurable until the event unfolds. Coming nearer than the altitude of geostationary satellites, this passage offers a groundbreaking chance for scientific study. Observatories will monitor Apophis nonstop during its approach, assessing its spin dynamics, charting its terrain, analyzing its makeup via spectral analysis, and gauging its dimensions and contours through radar observations. With a diameter of about 370 meters, the asteroid is sizable enough to wreak havoc on a regional scale in the event of a collision, yet compact enough that spotting fine surface details from ground-based instruments proves difficult. This proximity allows access to observational methods typically used for near-Earth objects in even tighter passages. Radar observations will be pivotal. Facilities such as California's Goldstone Array and the successor to Arecibo, provided it's ready by that time, will transmit radio signals toward the asteroid's exterior and examine the returning signals. Such radar yields exact range data down to the meter, spin cycle estimates precise to the second, and terrain texture details beyond the reach of visual telescopes. Delay Doppler radar techniques produce two-dimensional maps, with one dimension capturing the echo's time lag for range and the other its frequency shift for speed. These scans uncover the object's form, spin patterns, and topographic elements, occasionally spotting rocks, depressions, and elevations just a few meters wide. Examining spin is vital, as asteroids rotate, and their rotational behaviors reveal clues about their past. Apophis spins once every roughly 30 hours, a rate derived from light curve data that tracks brightness fluctuations as various sections reflect solar light back to our planet. The current spin seems steady, yet the 2029 Earth flyby will alter it. Gravitational tides exerted by our planet during the pass will tweak the asteroid's rotation, possibly accelerating or decelerating it based on the alignment. Tracking this shift yields insights into the body's core makeup, whether it's a cohesive rock or a loose aggregate of fragments bound mainly by self-gravity. The Yarkovsky effect introduces further intricacies. Asteroids soak up solar radiation, heating their exteriors, before emitting it as infrared warmth. This emitted heat imparts thrust, mimicking a minuscule propulsion system that nudges the body. On a spinning asteroid, the sunlit side heats more than the shaded one, leading to uneven thermal output that generates a subtle, ongoing push, either hastening or hindering orbital motion, contingent on whether the spin aligns with or opposes its path. Across eons, the Yarkovsky mechanism can reshape orbits dramatically, propelling objects from the asteroid belt toward Earth-intersecting paths. In Apophis's case, accurately quantifying this effect is essential for forecasting its extended orbital path. Though minuscule, causing just meters of drift annually, these shifts build up over time into kilometers of positional ambiguity. The 2029 encounter enables direct gauging of Yarkovsky acceleration by pitting the asteroid's observed location against models excluding thermal influences. Any mismatch signals the effect's presence, refining simulations for anticipating later flybys. Shaping public views poses both hurdles and prospects. Apophis has featured prominently in media since its initial detection, often framed with dire warnings of destructive rocks and celestial dangers. In reality, the odds of collision for all projected passes are minimal to non-existent, yet conveying such risks effectively remains tricky. Describing a 1 in 45,000 impact probability for 2068, the prevailing figure, can mean varied things to audiences. Experts in statistics view it as trivial, dwarfed by everyday hazards we routinely ignore. Yet for those less versed in odds, that fraction might seem worrisome, evoking a tangible threat instead of a virtually non-existent one. Ideas for Apophis expeditions have gained traction among planetary protection specialists. Dispatching a probe to meet the asteroid around or following its 2029 Earth pass would yield intimate observations unattainable from afar. Such a venture could detail the object's material, inner build, and exterior traits comprehensively. It might also test planetary defense methods, like kinetic impacts or gravity tractors, to gently adjust Apophis's path, affirming humanity's ability to safeguard against impending cosmic hazards. NASA's DART mission, the Double Asteroid Redirection Test, achieved a successful strike on Dimorphos in 2022, proving testing kinetic deflection performed just as expected. The collision adjusted Dimorphos's path around its bigger partner Didymos, demonstrating that people can modify asteroid courses with enough advance notice. The APIS initiative would expand upon DART's achievements, experimenting with redirection methods on a bigger, possibly more captivating scientific subject. Theories claiming NASA minimized the chances of collision are inevitable yet baseless, though they make sense from a mental standpoint. Organizations in space must navigate the tricky line between openness and preventing widespread fear. Sharing each initial trajectory estimate along with its margins for error can spark unnecessary worry, especially when those margins are wide. Such broad uncertainties are typical for recently spotted bodies with sparse observation records. Yet holding off on public statements until the data sharpens could lead to charges of secrecy if an outsider spots the object or information slips out. NASA and similar groups have leaned toward openness overall, sharing trajectory data and collision risks via the Sentry platform and Torino scale. Still, being upfront doesn't eliminate wild speculations. It merely redirects them from hiding collisions to concealing redirection mishaps or extraterrestrial meddling. The storyline of the asteroid grazing Earth's edge neatly blends risk with awe. Such near misses stir excitement. Apis won't strike us, yet it will draw near sufficient to make us sense its approach, observe its transit, and witness the stellar processes that sometimes send mountain-like boulders toward our planet. This proximity highlights that the void isn't vacant. Remnants from the solar system's birth continue circling, now and then intersecting Earth's route. And while we've dodged trouble to date, good fortune isn't infinite. Readiness counts. Systems for spotting, monitoring, analyzing, and redirecting offer our species a safeguard against the universe's random strikes that will strike someday. This occurrence also acts as a worldwide lesson. Defending against planetary threats demands global teamwork. Asteroids ignore national lines, and a danger to one country endangers everyone. The United Nations Committee on the Peaceful Uses of Outer Space oversees joint initiatives to monitor near-Earth objects and build countermeasure tools. The 2029 APIS Passover should spark fresh focus on funding and strategies for planetary protection, possibly speeding up advances in spotting arrays and redirection tools. Glancing toward the 2040 celestial lineup adds perspective. The cosmos follows timelines that disregard our clocks. Asteroids show up per orbital rules. Worlds form patterns based on Kepler's principles. Comets descend from the Oort cloud due to pulls that began ages past. We note these happenings in planners, looking forward to them, gearing up for them. Yet they play out by natural laws, not our whims. Apophis will glide by in 2029 no matter if we're observing, interested, or set. The universe's apathy toward our worries is equally frightening and freeing. Part 12. When Worlds Waltz, September 20th, 2040. Jot it down in whichever date system endures the years in between. as on that day the solar system will showcase a spatial setup uncommon enough to draw eyes, but frequent enough that like patterns repeat on known cycles. 6 worlds: Mercury, Venus, Mars, Jupiter, Saturn, and Uranus will gather in a slim strip of the heavens from our viewpoint. Their ecliptic longitudes, the angles tracing the sun's orbital path, will span under 90 degrees. News outlets will surely label it a planetary lineup or procession, even if strictly speaking, the bodies won't form a precise row. They'll just bunch up in a single sky sector, all viewable at once from Earth's dark half. Here's how the setup functions. The planets circle the sun in nearly the same flat disk, the ecliptic, set by our own orbital tilt. In our view, they seem to travel a route through the stars matching the zodiac signs. At times, the planets the full circle, popping up variously as Earth spins. On other occasions, their paths bunch up, letting several shine in the same sky patch together. These groupings happen periodically, but unevenly. They stem from bodies with varied revolution times, sometimes syncing their spots. How scarce it is hinges on the number of planets involved and the strictness of the cluster definition. Fitting all 8 into a 90 degrees arc occurs every several decades. Squeezing them into 30 degrees comes around every few hundred years. Achieving a true linear formation, every planet at 0-degree gaps from the sun's vantage, likely never materializes over human eras since their cycles lack the precise whole number matches needed for such precision. Ideal recurring planetary groupings. The 2040 conjunction stands out as especially promising for viewers since the gathering will feature prominent planets visible to the unaided eye. Mercury, Venus, Mars, Jupiter, and Saturn, all readily observable without any equipment, along with Uranus, which calls for binoculars or modest telescopes. Neptune, meanwhile, stays apart in its path, skipping the assembly. These worlds will appear in the post-sunset evening heavens, emerging as a group in the eastern direction and sweeping over the southern expanse, varying by the watcher's location on Earth, offering extended periods for stargazing. Hobbyists in astronomy are in for a treat. Snapping a broad-view photo that includes every noticeable planet turns feasible in such gatherings, yielding shots that highlight the layout of our solar system. The varying intensities and hues of these bodies add captivating details. Venus gleams in stark white. Mars shows a clear orange-red tint. Jupiter glows in yellowish white. Saturn echoes Jupiter, yet appears a bit dimmer. And Uranus emerges as a faint blue-green spot, hardly discernible even through binoculars. Grouping them in one image crafts a snapshot of cosmic variety squeezed into a lone composition. Experts in the field will grab chances that go further than mere scenic shots. Such lineups don't generate unique gravitational impacts, contrary to ongoing folklore about tidal pulls or quake initiations. Yet they enable coordinated observations of several worlds at once with identical tools and methods. This aids comparative studies of planets. Assessing the atmospheres of Venus, Jupiter, and Saturn in a single session minimizes equipment and viewing inconsistencies, leading to more reliable assessments. The lineup could also open doors to spotting oddities. As planets bunch up, the stellar backdrop in that zone draws extra scrutiny. Dim asteroids, far-off comets, or perhaps unseen outer solar system bodies could turn up from those surveying the area for the main attractions. The theorized Planet 9, suggested to account for the bunching orbits of remote trans-Neptunian objects, eludes detection despite hunts. Its forecasted position, assuming it exists, drifts gradually across the zodiac, and it could align near the 2040 cluster zone, boosting odds of finding it just because more scopes will aim there. Throughout history, human societies have woven myths and traditions around these celestial huddles. Early sky watchers monitored planetary paths closely, marking meetings and formations, and imbued them with deep importance. Astrology, enduring sans empirical backing, interprets these setups via symbols and supposed links. Modern science dismisses such ties as mere hunts for patterns and chance events. Still, our innate reaction to sky gatherings holds firm. A planetary roundup in one sky sector seems momentous, even as we rationally grasp its orbital mechanics at play. Certain marginal groups are bound to forecast dire outcomes from the 2040 event. Claims of planetary tugs sparking quakes or storms echo familiar apocalypse tales, devoid of physical basis. Planets' pull on Earth pales beside that of the Moon and Sunday. Even in unison, their collective force induces minuscule wobbles in our path, without detectable sway on land or air dynamics. Yet evidence rarely halts prophecies. Online, somebody will assert the grouping heralds calamities, drawing believers who stockpile, only for the warnings to fade or get excused when nothing happens. Beyond the obvious, these events hide chances for probing solar system mass layouts. Accurate monitoring of world positions lets scientists probe gravity models and fine-tune body weights. Each planet tugs on the others, building orbital deviations that build up gradually. By noting actual spots versus Newtonian forecasts, experts spot irregularities that could signal hidden masses or, more boldly, breaks in gravity laws. In our linked-up era, the worldwide aspect of these spectacles counts heavily. Distinct from eclipses, which demand precise locales for visibility, planetary setups shine for all, barring clouds. This fosters collective, awe-spanning societies and lands. Come 2040, folks in Tokyo, New York, Sydney, and Lagos will witness identical celestial patterns, forging a universal cosmic bond that surpasses boundaries. Political and cultural divides fade into the background. The idea of a celestial orchestra fits as a vivid analogy. Every planet follows its unique pace. Mercury zips around the Sun in just 88 days. Neptune, by contrast, takes a leisurely 165 years to complete one loop. Such varied cycles generate intricate harmonies and configurations across the ages. Planetary gatherings resemble instances in an expansive space opera where various voices blend at once, forming a resonant harmony before scattering back to solitary tunes. We shouldn't stretch the analogy excessively, since planets produce no audible tones or compositions, yet it aptly reflects the essence of recurring motifs and cadences in celestial paths. Hinting at the 2015 supermoon builds a thread through the storyline. Such conjunctions and near encounters serve as timeless markers that outlast personal lives. A child born in 2040 would be 12 at the supermoon's arrival, 20 during Apophis's flyby, and well into adulthood by the subsequent big planetary gathering. These stellar happenings act as milestones in collective recollection, communal moments that shape periods and organize chronology past mere human divisions like decades or centuries. Part 13. The Moon Brushing Against Earth. On November 9, 2022, we'll witness the tightest lunar encounter of the 21st century. A supermoon so remarkable it challenges the boundaries of the label. Earth's satellite follows an oval path, not a perfect circle. As a result, the separation between Earth and Moon fluctuates from roughly 363,000 kilometers at perigee, the nearest point, to about 405,000 kilometers at apogee, the farthest. This fluctuation alters how large the Moon looks from our viewpoint. Whenever it hits perigee while fully illuminated, looking its biggest and most radiant, that's a supermoon. The 2022 event in November will happen at a remarkably tight perigee, pulling the Moon to around 356,500 kilometers from Earth's core. That's about 3% nearer than standard supermoons and roughly 6% closer than normal full moons. The percentage might seem minor, but keep in mind we're dealing with visual angles, where proximity affects scale in curved proportions. A 6% shorter distance yields a 13% bigger visible width and a 30% brighter glow. At this near point, the Moon will look substantial enough that the contrast with routine full moons stands out. No tools required. Set a snapshot of a 2022 full moon beside one from a typical range, and the variance jumps out. The supermoon occupies more sky. Its craters and seas seem more prominent. Its light bathes scenes with greater intensity. In clear skies with the Moon low on the horizon, the mix of its true enlargement and the horizon illusion, that mental trick enlarging low moons over high ones, will yield sights bordering on dreamlike. Photographers will find unmatched chances. Moon shooters eagerly await supermoons to frame them with earthly landmarks, leveraging the extra scale for striking setups. The 2022 occasion offers the pinnacle for today's image makers. Preparations will begin far ahead, surveying spots where the moon emerges or dips behind compelling backdrops, figuring precise moments and angles for the perfect capture. The added luminosity brings impacts past mere beauty. Regular moonlight suffices to throw shadows and sway nighttime wildlife habits. Supermoon rays, even stronger, could etch clear silhouettes from items and light up terrains nearly like dusk. Night creatures synced to moon cycles may react to the exceptional illumination. Sight-dependent hunters could gain an edge against quarry hiding in shadows. Hunted animals might shift patterns, hunkering down through peak glow times. The biggest tangible outcome from such lunar near misses lies in intensified tides. Sea surges stem from gravity's pull differences. The moon tugs unevenly on Earth's near and far sides. This pull difference forms dual bulges, one toward the moon and one away. Earth's spin then sweeps shores past these swells, yielding the standard 2 highs and lows per day. Tide power hinges on lunar proximity. Nearer pulls mean steeper gradients and taller surges. King tides, the peaks at new or full moon when sun and moon team up, get boosted in the 2015 supermoon. Shorelines prone to strong king tides could face rises a few centimeters above normal. It may not seem like much, but amid stormy high waters, those added centimeters could tip the balance from contained flows to breaches over barriers and inundation of seaside zones. Infrastructure plays a key role here. Authorities are expected to release alerts for coastal flooding in at-risk zones, especially regions grappling with rising seas due to global warming. Theories about seismic interactions delve into more uncertain ground. Certain scientists have examined links between moon phases and tidal pulls with quake events, seeking signs that tidal pressure on fault lines could spark tremors on the verge of rupture. The prevailing view holds that any influence like this, should it be present, is practically insignificant. Earthquakes occur when built-up tectonic forces surpass the friction keeping faults in place. By contrast, tidal forces are vastly weaker than those tectonic ones. That said, for faults teetering on the edge, even minor extra strains could in theory act as the spark. Research has spotted faint ties between tides and quakes in certain fault networks, though not in all. These impacts are so minor that they're hard to distinguish from random fluctuations. The 2022 supermoon offers a real-world test case. Should tidal triggering prove detectable, we could see a modest uptick in global quake activity near the time of peak proximity. If levels stay typical, it reinforces the idea that tides have little bearing on seismic events. Public reactions to the supermoon will probably mix excitement with worry. Gatherings and watch parties will pull people to clear sky spots and iconic sites. When supermoons align with lunar eclipses, they turn into major broadcasts, drawing huge audiences. Absent an eclipse, the unprecedented scale of the 2052 occurrence will still spark buzz. At the same time, online rumors of end-time scenarios and dire prophecies will spread, insisting the near-past signals catastrophe. Such claims follow familiar scripts and will prove just as unfounded as before, yet they'll snag some notice and stir needless fear in those not versed in celestial basics. The saying about a night shining like daylight overstates it, but it conveys the essence of intensely vivid lunar glow. Our eyes adjust to low light, with pupils widening to capture more rays and light-sensitive cells ramping up responsiveness. In full dark mode, the human eye's light detection covers a vast spectrum. Regular full moonlight lets you navigate easily, scan bold text, and discern hues faintly. Supermoon light amps this up, possibly enabling standard reading and sharper color perception. Paired with crisp air and minimal ambient glow, it nears the brightness of late dusk. Probes into air scattering gain from strong moonlight, as the moon's steady beam serves as a reliable tool for gauging sky conditions. Teams probing particles, vapor layers, and air makeup often leverage moonlight for checks or to stretch data collection past sunset. The supermoon delivers exceptional intensity, which might yield finer readings or spot faint signals usually lost in the background. Grassroots science efforts could rally worldwide supermoon sightings, gathering notes on perceived glow, tint, and sky influences from participants everywhere. Past initiatives have gathered eclipse logs, shooting star tallies, and northern lights sightings, creating archives that aid experts while boosting astronomy enthusiasm. The supermoon stands out as an easy-to-spot event, open to viewing and snapping by all, easing entry for newcomers. Shifting to comets that could eclipse this supermoon's shine lays the groundwork for the closing story arcs. At its nearest, the moon will dazzle, yet it's a routine cycle, the peak in an ongoing string of monthly supermoons of differing strengths. Comets, however, are the unpredictables, rare intruders that sometimes match or top the moon's radiance, though on no set timetable. This contrast underscores varied heavenly displays, the steady loops of orbit-bound bodies against the erratic bursts of comets plunging in from the void's fringes. Part 14. 2060. The most brilliant comet on record. In 2060, an unprecedented sight awaits the living. Projections are set, paths computed, and stargazers are already noting the date for a spectacle to match history's grandest. A colossal body from the Oort cloud, that far-off comet stockpile encircling our system, barrels toward the sun's core along a path slinging it near enough to blaze fiercely. Not merely vivid or noticeable, but perhaps rivaling the moon's own glow, commanding the for weeks, or maybe even months. This comet could light up the evening heavens. Should the forecasts prove accurate, it promises to be the standout celestial phenomenon of our era, a rare wonder visible during the day, throwing shadows after dark, and reshaping how we all connect with the stars above. To give you some context, the majority of comets swinging into the inner solar system are dim, needing binoculars or scopes for a glimpse. A few per decade show up to the unaided eye as hazy glows with subtle trails. Roughly every several decades, a vivid one emerges, grabbing news cycles and luring crowds to gaze skyward. Take Comet Hale-Bopp in 1997. It lingered for more than 18 months and shone so clearly that urban dwellers could spot it amid light pollution. Earlier, Comet West in 1976 delivered an awe-inspiring display for early risers catching it pre-dawn. And don't forget Halley's Comet, cycling back every 75 to 76 years, chronicled by civilizations for over 2,000 years, from Babylonian archives and Chinese annals to the Bayeux Tapestry. Yet even Halley's at peak is merely a striking visitor. It's captivating, no doubt, but it doesn't command the firmament. This 2060 comet, if it delivers on expectations, will seize total control. Projections indicate it might hit an apparent magnitude of -10 or brighter still at -12, rivaling the glow of a quarter moon or even a full one. Grasping the scale requires understanding that magnitudes work logarithmically and inversely. The sun clocks in at -26. 7. A full moon registers -2. 7. Venus at maximum dazzle reaches about -4. 9. A luminous comet like Hale-Bopp peaked near -1. Each interval packs about 2.5 times the illumination. Thus, a -10 magnitude isn't merely double Hale-Bopp's shine. It's exponentially more intense, by thousands of factors. What fuels such a dazzling display? Scale plays a key role. The 2060 comet's core is projected to be massively large, perhaps 50 to 100 kilometers wide, ranking among the biggest intruders from the Oort cloud into our neighborhood. By contrast, Hale-Bopp's nucleus measured around 60 kilometers, which was already deemed gigantic. Still, bulk isn't everything. It must also venture near the sun, near enough for intense solar warmth to sublimate vast quantities of frozen material, forming a coma bigger than Jupiter and a tail extending across hundreds of millions of kilometers. The 2060 visitor ticks every criterion. Its closest solar approach, or perihelion, will dip to roughly 0.3 astronomical units, or about 45 million kilometers, tucked inside Mercury's path. There, the sun's energy won't just melt water ice, but also liberate more fragile substances like carbon monoxide and dioxide. Yet the implications stretch beyond astronomy. Something profound stirs. In 2060, for a fleeting interval, people worldwide will unite in wonder. Folks across nations and land masses will tilt their heads upward to behold the identical marvel, a blaze too intense to overlook, so mesmerizing it bridges tongues, traditions, and divides. The 2060 comet will be unmissable, ruling dusk and dark hours, piercing even city glare, and providing enough radiance in secluded spots to pore over a book. And this is where intrigue mixes with a touch of unease. What unfolds when a nighttime illuminator challenges the moon's reign? We recognize moonlight shapes wildlife patterns. Night creatures adapt to lunar cycles. Hunters shift tactics under full moons. Our built-in body clocks, dictating sleep patterns, respond to surrounding brightness. Throughout human history, the moon has held the night sky's top brightness spot. Introducing a new contender disrupts that balance. What effects follow? Honestly, it's uncharted territory. The comet's glow will endure for weeks, perhaps months, flooding the dark with unprecedented comet-sourced light in our records. Shifting to riskier angles, proximity to Earth always sparks fears of collisions and disasters. To clarify, the 2060 comet poses no collision threat. Its trajectory is precisely mapped, passing us by millions of kilometers. That said, it's not without ripple effects. As comets near the sun, they release bits, dust, tiny bits, occasionally bigger chunks, that disperse along their path. Should our orbit cross this trail post-passage, it might spark a dazzling meteor display. More worrisome, though improbable, is fragmentation. Comets can splinter under solar proximity, from heat strain, gravitational pulls, explosive gas releases, or structural weaknesses. Draw a visitor into the core of a comet. Should the 2060 comet break apart, and should a piece of it follow a path nearer to our planet than expected, that could spell trouble. The chances remain incredibly slim, yet far from zero. That's precisely why monitoring asteroids and comets has turned into a vital pursuit. Still, the main reaction ought to be wonder, since no matter what, the 2060 comet promises to be stunning. It serves as a vivid cue that our cosmos holds the power to produce breathtaking events. Over several weeks or months, chats at the dinner table might touch on the makeup of its tail and the behavior of its coma. Kids will linger awake to catch a glimpse of it. The comet will weave itself into the shared experiences of that era. Once it concludes, after looping past the sun and retreating to the solar system's fringes, we'll hold on to images and recollections. Yet even as it dims, another marker on the astronomical timeline looms with similar depth. Part 15, 2177, Pluto's inaugural anniversary and a moment for universal contemplation. On February 18, 1930, a budding stargazer called Clyde Toomer scrutinized photo plates at the Lowell Observatory in Flagstaff, Arizona. His goal was to locate the anticipated ninth planet, a realm past Neptune that could account for minor wobbles in the distant world's paths. The task dragged on, involving side-by-side views from exposures separated by days, scanning for shifts amid the starry backdrop. Suddenly, there it was, a faint speck that had relocated between the shots. Planet X, the ninth world, Pluto. News of the find spread globally in bold print. Pluto marked the initial planet unearthed by an American, igniting public fascination in a manner few celestial finds achieve. The moniker Pluto, proposed by an 11-year-old English girl named Venetia Burney, fit ideally. The deity of the realm below suited this remote, shadowy outpost at the solar system's boundary. For 76 years, youngsters memorized that our system boasted 9 worlds. Pluto, small and enigmatic, stood as the final sentinel before the vast void of interplanetary emptiness. Then, in 2006, the International Astronomical Union revised the definition of a planet. Pluto satisfied 2 out of 3 standards, but missed the last. It hadn't swept its orbital zone free of stray objects. By this updated rule, Pluto shifted to dwarf planet status, reducing the system to 8 once more. The downgrade sparked unexpected widespread dismay. Folks harbored fondness for Pluto, that far-off scrappy sphere. But consider this angle that reframes it all. In 2177, precisely 247 years post-discovery, Pluto will finish its full loop around the Sun. It will reclaim the exact spot in the heavens where Clyde Toomer first detected it on those photo plates. Ponder the implications. Pluto's year, one full revolution, spans 247. 9 Earth years. Back in 1930 at its unveiling, Pluto had covered roughly 36% of a single orbit since the Declaration of Independence. We've observed Pluto, probed it, dispatched a probe for a close pass in 2015, witnessed its downgrade, and fueled endless debates. All the while, Pluto hasn't circled the Sun even once. This drives home a deep insight into temporal dimensions. Humans endure roughly 80 to 100 years at most. That's the reach of personal recall and first-hand encounters for anyone. Societies endure further, with unbroken documented history stretching about 5,000 years. Yet even there, Pluto has managed only around 20 circuits. The full arc of human culture equates to merely 20 solar journeys for this far-flung body. Expand the view to the solar system's 4.5 billion-year saga, and Pluto has notched about 18 million laps. That figure seems immense, until you note Earth has logged 4.5 billion in the identical period. Beyond Pluto, the outer realms function on durations that eclipse our grasp. Neptune requires 165 years per sun circuit. From its 1846 reveal, it has barely edged past one full turn. Uranus demands 84 years. Saturn, 29. These giants traverse the constellations with a dignified, barely detectable rhythm. Early sky watchers recognized just 5 planets past Earth, as only those shift visibly across the firmament over a person's span. And that prompts a compelling query. What's the greatest time frame our species can authentically internalize? We can rationally absorb that the cosmos dates to 13.8 billion years, the sun to 4.5 billion. We can quote these figures, embed them in books, instruct the young. But do we truly internalize them? Can any mind encompass 13 billion years in a tangible sense? Likely not. Our instincts tune to individual spans, the decades we anticipate. Past a handful of lineages, duration turns vague. That's precisely why Pluto's inaugural orbit completion post-discovery serves as such a touching milestone. It's a time frame that's only just within the grasp of our society's understanding. A 247-year cycle stretches from 1930 to 2177, projecting more than 150 years ahead into our future. It exceeds the span of any individual's lifespan, outlasts the endurance of most organizations, yet remains concise enough to allow us to follow threads of cultural legacy. Folks in 2177 will have access to archives from the era of Pluto's unveiling and grasp the pursuits of those early stargazers, along with their significance. Yet as Pluto wraps up that initial loop in 2177, it'll merely kick off its next revolution around the sun since being spotted. That follow-up circuit will demand yet another 247 years. Pluto won't finish a third pass until 2671. The individuals set to observe Pluto's second such event aren't even born and won't arrive on the scene for generations. By that point, though, will humanity retain its fascination with Pluto? Will we continue scanning the heavens, monitoring planetary paths, and noting these vast celestial events? I hope so. Even amid the turmoil that so often defines our actions, we've sustained sky-watching facilities for ages. We've archived data, handed off insights, and expanded upon the breakthroughs of those who came before. Our ability to forecast Pluto's trajectory and pinpoint its location in 2177 stands as powerful evidence of collective human wisdom, forged over eras in pursuit of shared objectives. And on the topic of expansive timelines, ponder this. When 3I Atlas arrived in our solar system in 2024, it had traversed the emptiness between stars for eons. Should it have originated from a stellar neighborhood 10 light-years distant, cruising at 66 kilometers per second, the voyage would have lasted roughly 45,000 years. Throughout that vast duration, the comet stayed iced over, unaltered, wandering the emptiness. Then it lingered briefly in our neighborhood, met its end via solar destruction, and vanished. Still, comprehension differs from true sensation. We might compute Pluto's path, but we can't truly sense the weight of 247 years encircling the sun. We can quantify the star's existence at 10 billion years, yet fail to intuitively seize that immense duration. Our existence is hemmed in by our physical limits, our finite days, and our spot within the cosmos and chronology. When Clyde Toomer spotted Pluto in 1930, he was merely 24. He passed away in 1997 at 90. Having witnessed probes explore each world in our system and humanity's steps on the lunar surface. But he never beheld Pluto finishing a single orbit. None of the people alive at the moment of Pluto's detection will endure to mark its first such completion. that event will fall to generations still unborn.